Welcome everyone to the iWest seminar series. My name is Andrea Maestas. I'm part of the iWest team at Los Alamos National Lab, and I'll be your host for today. I'll start with a brief introduction to iWest for anyone who may be joining for the first time. iWest is an initiative funded by the U.S. Department of Energy to provide communities across 6 Intermountain West states with data, tools, and information for energy transition planning. iWest takes a place-based approach, which frames everything we do in the context of the geographical, environmental, and demographic attributes of the Intermountain West region. And we also take a technology-neutral approach that explores energy options and opportunities across numerous symbiotic energy economies. Those technologies are assessed in tandem with societal readiness, which we believe is key to ensuring an equitable energy transition. And those assessments are all done through community engagement and coalition building to encourage regional partnerships. Today's seminar is focused on scientific approaches to reducing the impact of undocumented orphan wells, which is an issue of high importance to many energy communities in the iWest region. It's my pleasure to introduce our speaker for today, Dr. Hari Viswanathan. Hari is a senior scientist in the Energy and Natural Resources Security Group at Los Alamos National Lab, where he leads several energy security projects on behalf of the U.S. Department of Energy, including serving as the technical lead of the catalog program, which is something we'll learn about today. Hari has expertise in subsurface fractured systems, reservoir modeling, and machine learning, all of which are critical elements for characterizing subsurface systems. Hari has received numerous recognitions for his work in these areas. He's a GSA Fellow, Los Alamos National Lab Fellow, and winner of the Los Alamos Fellows Prize for Outstanding Research. Thanks so much for being with us today, Hari. And with that, I'll let you take it away.
Okay, yeah, thanks for the opportunity to present. We have a 5-lag program called Catalog that's looking for undocumented orphan wells, and so I'll describe what we've been up to. This came out of the infrastructure bill, and then it's received additional funding from the Build Back Better. And we have 5 different national labs working on this challenging program, which I'll go through. So next slide. Yeah, so I thought I would try to tie in how I think this fits into iWest quite a bit, because we know that iWest is trying to support, all these different regional projects, both from a techno-economic and life cycle analysis, whether we're storage, utilization, conversion. I mean, these are all things that we're looking at for the energy transition to try to get to net zero, and also how to connect community, all the disparate industries that play in the iWest region. And, there's so many different end users, research institutes, initiatives that make up this research corridor. And we think it's a real test bed for energy transition that is going to be taking place worldwide. And so clearly, one of the things for being able to get to net zero is definitely reducing CO2 emissions, but also reducing methane emissions, because those are both, really bad global warming gases. And definitely places like the Four Corners, which is a methane hotspot. These are areas where, dealing with methane emissions that come from a lot of different sources. They come from agriculture, active oil and gas wells, but the program that I'm going to be talking about is undocumented orphan wells, and I'll explain what that is. But the technologies that we're trying to stand up using undocumented orphan wells apply to many other, methane emissions as well, and other types of emissions. Next slide. Yeah, so since the Biden administration came in, actually, what was just DOE fossil energy has completely been reorganized, and it's now fossil energy carbon management. And now there's an entire branch of DOE fossil energy carbon management that is just on methane mitigation because it's being recognized as, a huge thing that can be done in the short term to really get to the administration's goals, both at 2030 and 2050. And so the way DOE FECM is organized is there's methane emissions mitigation, methane emissions quantification, decarbonization of natural gas resources, and then actually part of this whole thing is undocumented orphan wells, which is what we have a program that I'm going to talk about today. But as I said, the type of technologies that we're developing for undocumented orphan wells are quite applicable to the other three as well. So next slide. And so what came out of the bipartisan infrastructure bill, and it's basically written in there explicitly, is to basically conduct research and development activities working with the Interstate Oil and Gas Commission. And the Interstate Oil and Gas Compact Commission has a bunch of different state representatives. And the goal is to assist, federal land management agencies, states, and Indian tribes, and to identify and characterize undocumented orphan wells, and then to also mitigate their environmental risks. And so for those of you that may not even know about undocumented orphan wells, there's the estimate on the right-hand side of between 310,000 to 800,000 in the US is actually a very conservative estimate. There's another one that the EPA did that has roughly like 2 million undocumented orphan wells. And so what these are wells that there were quite a few drilled even between 1850 and 1950. And before 1950, there were a lot fewer regulations. And so people were putting oil and gas wells in wherever they could, where they thought there was oil and gas, and there was not really a strict code in how to put all of these wells in. And as you could imagine, that meant that you're going to get all different types of wells, different levels of construction. And you could imagine that many of those companies have since gone bankrupt. And the reason these are called orphan wells is there is no company that's actually on the hook to do anything about these wells. And so it sort of goes to the government to have to deal with these wells. Another thing, if you're not as familiar with, just what can leak from the subsurface and so on, the subsurface is actually a pretty good natural barrier in many cases from things to leak a huge distance. But when you go and drill a well, obviously the goal is to perforate all those barriers so you can extract a resource. And so once you've put all those wells into place, there's a good chance that they're going to be leaking things like, for example, methane, which is a bad global warming, warming gas. But then on top of that, a gas is going to move faster than a liquid, but you could easily also have liquid contaminants that are contaminating the groundwater and things like that. And so these wells are definitely scattered all over the country, as I'll show. And the thing that's very difficult about finding them is the pictures on the right-hand side. You would be able to find those, right? Because you can see them at the surface. They're not overgrown by vegetation, but there's going to be many cases where there is nothing that you can see at the surface. There's just a pipe that's actually underground, and there may be nothing that you can see on the surface. And then you might say, well, why can't you just look at, use a magnetometer to find the metal? That can also be quite complicated in many cases because the signal may be pretty weak. And then for these wells, there's actually a large number during World War II where they took all the metal casing out and used it for World War II purposes. And so there isn't even metal in some cases. And so actually finding these wells has turned out to be a really challenging problem. And when I first got put in charge of this program, I didn't expect it to be as challenging as it is. And so what we have under the infrastructure bill is 5 years, $30 million to basically come up with best practices for the states to find how are you going to find these wells and characterize them to a minimal amount. What makes this 5 million, the 30 million so exciting though, is that it goes to advise and to help the Department of Interior that's been given $4.7 billion to deal with these wells. And so it's been a really good interagency collaboration. We meet with the Department of Interior almost every week, and there's White House involvement. And so, yeah, it's been a real pleasure to be part of this program. And there's quite a few cutting edge science aspects to it, but it's also quite societally impactful. And in addition to just getting the infrastructure bill money, there's additional appropriations that we expect to keep coming in year after year. So last year we got 10 million that was separate from just the infrastructure bill. That's expected to repeat this next year. And so that's how this program has been stood up. So next slide. And so the way this was set up, even according to the infrastructure bill, is they knew that the national labs would have to get involved because, like I said, the wells, even before this program started, it was very much known that quite a few of them are not that easy to find. And there are reasons where you can, you have to collect multiple signatures. These signatures tend to be very noisy, using things like machine learning to try to extract signal from noise. Those are all things that the different national labs are sort of at the forefront of. And also we have a lot of expertise in characterization of the subsurface and the surface that is right in line with this program. And then being able to detect these wells is something that we've been doing at smaller efforts with different labs, but nothing as coherent as this program is putting forward. And so for us to be successful, we just need to be able to come up with, what is a set of best practices and work with the states and show them how to roll this out. And, unlike some programs I've been part of, this one's pretty straightforward. We need to find wells. We need to move them from the undocumented column over to the documented column, and we want to work with the states and the Department of Interior so they can use that 4.7 billion appropriately to plug and abandon these wells. And so the way this is happening to actually reach out to the states is with the IOGCC, which is the Interstate Oil and Gas Compact Commission that I was talking about. They have different representative from each state that has oil and gas, going on in their state. And so we meet with them about once a month now, and we sort of figure out what are their needs, and then we sort of tell them what we're doing. And so that's been going pretty well so far. And actually, before we stood up this program, we started with a survey to figure out what their needs are, so we don't just go and do something that's completely impractical. And then the key for this, where the real money to actually plug and abandon them are these Department of Interior funds, which is 4.7 billion, which might seem like a large amount of money, but actually, if you look at the number of wells that are out there, it's actually just the beginning of what's needed to deal with a lot of these wells. So there has to be quite a bit of prioritization, because some of them are really not necessarily causing much problems, and there's other ones that are leaking and quite problematic. And so how to go about that prioritization is a lot of what we're dealing with as well. Next slide. And so, like I said, we started out just making sure that we go after the kind of things that the states actually care about, right? So we survey, and we had 30 state representatives, which had a heavy oil and gas footprint. And one thing that's a bit tricky about this is they already have a huge list of documented orphan wells to deal with that they already know are a problem. So in a sense, our undocumented orphan well program is just adding to their list. And so in a sense, they're not able, they already haven't been able to deal with the ones they have, but they also realize that there's more, and some of the ones that haven't been identified actually may be quite problematic. And so we asked them, what have they been doing so far to kind of find these undocumented orphan wells? And, maybe not surprisingly, historical records are something that they rely on quite a bit. But if you imagine that some of these wells are back from like the 1850s or 1900s, the historical records are actually are very heterogeneous, and a lot of them are not in great shape. And yeah, so even being able to extract information from those historical records is something that we're using AI for, which is a different type of AI than I've been used to using so far. The other big thing that they've been doing so far is just a landowner is going to find, that there's something in their backyard that may be problematic. Actually, just within the last month, if you were watching the nightly news on NBC, there was, a house that caught fire in Pennsylvania, and it looks like there was an undocumented orphan well there. And for those that may not be as familiar with this problem, undocumented orphan wells in places like Pennsylvania and New York, they've got a crazy number of wells because that's where oil and gas initially started, and they basically didn't even think about interference too much of one well to the next. And so I'll show you later, there's some areas which are just littered with a huge number of wells, and they actually have a lot on their hands trying to deal with those. And so landowner complaints has sort of been the way they've been going about it so far. And so they're not, for example, like where we're heading, which is using things like drones and putting sensors on drones and mapping these things out. That's really not the way it's been done for the most part so far. And then there's also just been field inspections of different areas where people suspect that there's quite a few wells. When you ask people what are their gaps, what do they need to know? I mean, I guess the first really obvious one, maybe shouldn't be that surprising, is just where are these things? They don't know. And then, you need to know something about what is the construction on these wells if you want to successfully plug and abandon them. And also, what kind of integrity do they have? And so the current state of practice for this is that it is incredibly labor intensive, and it hasn't been that technical. It hasn't been using really like cutting edge techniques to find these things. And, I'll give you one little vignette. There's in West Virginia, there's Jackson State Park. And we were told that's a place we know that there's a large number of wells, and the historical records indicate that there should be quite a few wells in this area, but they don't know exactly where they are. And when we talked to the people who went about trying to find them, they said they can't find them. But when we asked them how they're looking, they were just kind of visually looking. I mean, they weren't using magnetometers or anything. And so there is some best practices that we think can be done quite economically to quite easily at least find some of these wells that are just not that challenging to find if you just go around with a drone and a magnetometer, for example. And so that's sort of where we saw that this is where the states were at when we started this, when we were standing it up. So next slide. And so we basically came up with 9 different areas to go after. And so we call the program Catalog, and we have a website, and we're adding more and more information, and that's where we want to have the best practices and so on. And since this is an iWest seminar, I should mention areas like the Four Corners and Hobbs and even the Permian Basin and, just in New Mexico, there's a huge footprint of not necessarily having anywhere close to the number of wells as Pennsylvania, Oklahoma, or New York. But then at the same time, we still do have quite a few wells that leak methane in certain areas, which are a pretty complicated patchwork of tribal land, federal land, and so on. And so there is quite a bit of interest in, even source attribution in the Four Corners because it is a methane hotspot. And there's different leaks of methane, and trying to figure out what's causing the leaks and so on is definitely, so the Four Corners is one of our test beds. And so these different priorities, it's actually a bit interesting because before Catalog came along, the people that looked for leakage of methane from wells were not necessarily the people trying to find the wells. It's 2 different sets of people. And as I'll get into later, a lot of this funding came in because the administration really wanted to start showing progress on, being able to mitigate climate change and so on, and knowing that methane would be something that's a really, warms far more, then, oh, I guess should I just hold the questions till the end, Rachel, or Andrea?
Yeah, let's hold questions until the end so
Okay.
we can get through your
Cool.
presentation.
Yeah, so I'll just point out that the people who are thinking about detecting methane from these wells have been very different than the people even trying to find the wells. And when they came up with the 4.7 billion from the infrastructure bill, some of this came to the forefront because states would have to apply to access that 4.7 billion. You would say, I'm going to apply for a grant, and I want to, because I have these wells that need to be dealt with. And in the first set of grants, the government knew that, being able to quantify how much methane mitigation occurred when you plugged a well was not something that's common practice. But now on the second round of grants, there's stricter language that DOI will be putting in that basically says when you plug a well, how much methane mitigation are you going to get? And the thing that kind of came out really quickly is that most plugging and abandonment companies don't even look at methane, for example. So I'll show a little vignette on how we tried to help that problem. So methane detection quantification, then number 2, which is just identifying the wells, whether they leak methane or not. And then a big part of, I think, why the national labs are really good for this problem is for many areas, not just this, we do lots of sensor fusion and data integration, meaning that we often, especially in the earth sciences, we know that there isn't just one signature that we can collect. Geophysics tends to be pretty noisy. And so you end up having to collect, for example, you could use magnetometer, you could use hyperspectral, you could use just photos, you could use methane for the ones that are leaking quite badly, but all of those are going to be quite noisy. And then how do you put all these noisy signals and then pull signal out of noise? And machine learning is something that has had a lot of success in being able to pull signal out of noise. And then characterizing these wells is also something we have a ton of expertise in. And I would say the first 4 all have to feed the integration and best practices, meaning that we need to be able to show the states, if you have suspect you have wells, this is the type of drone, and these are the type of sensors you would use. This is the pattern you would fly the drone. This is the height at which you would find the drone. This is the post-processing you can do to extract and figure out where these things are. And so those are the best practices that we have a list that we're already putting together. And then there's a whole database on this, which is basically making sure that the wells that we're finding are truly undocumented and not documented. And so there's actually a large database of oil and gas wells where we're adding these undocumented orphan wells and documenting them as orphan. So that's sort of that. And then the whole historical records is kind of an area that's very different from my expertise, which is more subsurface and reservoir modeling and machine learning. But it turns out that each state tends to have a large amount of paper records that are often in pretty poor shape, especially the old ones. And you can imagine they'd be covered with watermarks, and they may even be written by hand. And so you need to use optical character recognition to turn that into something digital. And then we're actually using some of these things like ChatGPT and so on to actually try to teach machine learning how to extract key information from some of these records as one thing we're trying. And then we're trying more brute force techniques, which would be like in Pennsylvania, the depth of the well is always in the bottom right-hand corner or something like that. And so we're, using multiple techniques to see what makes the most sense. And like I said, we have this overall database, and then a lot of the money goes to actually taking our field teams, which have like drone pilots, that are FAA authorized. And then we have different sensors on these drones. And just this summer, we've started doing this, going out to different areas and trying to find these wells, and then hopefully show states how they can continue to find these wells. So that's how the program's organized. And we've got Lawrence Berkeley, Lawrence Livermore, Los Alamos is the lead lab. I'm the lead on the whole thing. NETL actually has been doing a lot of work in this area even before this program started. And we've also got Sandia working on this. Next slide. And so, I mean, I think I was a bit naive when I first started looking at this problem. I really did just think how hard could it be? I mean, wells have a lot of metal and they go pretty deep, and seems like a magnetometer should do the trick. And this is just to emphasize why this is kind of a challenging yet very interesting problem from a scientific perspective. And so this is work that NETL did, and this is just a square kilometer where they actually used 5 different techniques to try to pinpoint where they know there's a bunch of undocumented orphan wells. And so things they use are magnetic survey, aerial satellite photography, LIDAR, some of these are leaking methane, some are not, historical records. And so in this particular case, you can see, even if you can't see the details, what it is that the dots don't line up. I mean, what comes out of like the USGS topographic map is different than what the LIDAR says, which is different than the magnetometer. It doesn't all just nicely reduce to the same point. It actually turns out to be just really noisy. And so definitely people who've worked in this space for a while all agree that no method just works in all cases. And so magnetics definitely are not going to work when the well casing is removed, but actually even just flying our drones around here in Los Alamos, there's a lot of like things that mess up a magnetometer. There were things that I never even understood. Like initially, if you fly a magnetometer and let's say you fly it over cars, or you put fire extinguishers out on a football field and you want to detect that, actually the magnetometer doesn't do a very good job of that. What it does a really good job of is detecting something that's a really long length of pipe. And so in this case, that's what a well is, a long length of pipe. But because of the topographic effects around here with all the canyons and the mountains and everything we have, how the elevation changes so much, it actually results in the magnetometer data being far more noisy than it is in places like Pennsylvania and New York. So when we go to some of our NETL experts who've had great success using it in flatter terrain, they're kind of shocked at how noisy some of our results are coming out to be here. And then we have really good methane measurement expertise at the different labs. And so finding out, being able to detect methane, and you can obviously get the super emitters, which are the ones that emit a really large amount. But later I'll show there's actually ones that emit a negligible amount of methane, and then there's super emitters. But unfortunately, there's a huge percentage of wells that emit methane that you do need to worry about, but it's low enough that it's not that easy to detect unless you're really close. And aerial photos and satellite photos actually it's interesting. The Google X that does all of their moonshots was here just a couple of weeks ago, and Google has great satellite information, which you usually have to pay for, and it would be very useful in areas which are not overgrown vegetation. But because this is a societally impactful project, that they might be working with us to share some of their higher resolution satellite data to help us find these wells in areas which are not overgrown by vegetation. And finally, like I was saying, as far as iWest is concerned, definitely the Four Corners area is one of our big test beds where we want to do this, because Lanel and Sandia are both in New Mexico, and we already know from Deb Holland has identified different wells there, and we're actually have been out there already and will continue going out there. And another area nearby that maybe not exactly iWest, but definitely in Oklahoma, the Osage. Oklahoma has a crazy number of undocumented orphan wells. Next slide. So I'll just kind of start going through some of these vignettes to sort of give you more concrete examples of what we've been doing. Next slide. Yeah, so this is a little what I was talking about when they first rolled all this out. The money kind of came quick, that states heard that there was, the $4.7 billion, but then plugging and abandonment companies really were not even in the business of trying to measure like a baseline methane and then how much mitigation you get when you plug a well. And so this last Christmas, this kind of became a big deal, because the companies were kind of coming back saying that it could cost almost like, initially it was $10,000 per well. It came down to about $2,500 per well to try to put a flux tower over these things and try to figure out how much methane is leaking out of these wells. And so the White House came to our program and basically said, rather than measuring methane flux coming out of these wells, could you actually take a concentration measurement and then estimate the flux, with uncertainty bounds, which would be a lot cheaper. And so that's something that we put work into, and the goal was to go from concentration to flow rate, especially for wells that are not leaking a large amount. And so the goal here was to develop a screening methodology for estimating flow rate from a cheap kind of handheld concentration measurement that would be technically defensible and would be a simple procedure and cost effective. And this is something we're working to get into the Department of Interior's language, where they set the guidance on methane. Next slide. And yeah, so if you would sort of wonder, like, how many of these things really are leaking methane, and what is a bad leak rate, and how do you sort these things? It's definitely true that there's really just a few super emitters that actually emit a crazy amount of methane, and those are actually pretty easy to detect and deal with, which is good news. However, the scientists that were not us basically set a rate of this 1 gram per hour leakage rate, and there's actually a large number of wells that kind of fall in between the easy to detect super emitter and the ones that are leaking enough that you still need to worry about it. So that's sort of what we're targeting. Next slide. And so what we wanted to do is basically figure out that clearly, if you just use a Gaussian plume model, over a large distance, that's not going to be particularly accurate, because we know how windy it is, and being able to go from concentration to flow rate is no easy thing. But in this case, we know where the well is, and we're able, if you can get quite close to it, in that case, the Gaussian plume model, under certain wind conditions, stable wind conditions, you can actually, do an inverse calculation with uncertainty quantification and do a pretty good mapping between concentration and flow rate. And so that's basically what we put together as a white paper to propose. And what you would do is you have where the well is leaking methane, and then you have a certain distance and certain parameters, and you basically detect what the concentration is going to be. And go to the next slide, please. And so what you do is you can basically come up with a relationship between concentration and flow rate at a bunch of different wind speeds. And what we're doing here is just using simple Gaussian plume models, inverse analysis, and uncertainty quantification to develop this relationship between concentration and flow rate. And so we've got this relationship, and now we've got our field teams out there actually measuring whether this relationship works, and so far so good. One thing to just point out, though, is you can see a horizontal line which says cow. So that really is what a single cow is going to emit in methane, right? So that gives you an idea that there are quite a few wells that are emitting a lot less than a cow. And so that puts things in perspective. However, there's other wells that leak quite a bit more. And so we do want to be practical, because there does need to be a prioritization based on the number of wells there are. So this was actually kind of a nice, I think, interagency collaboration, because we were able to talk to the Department of Interior, sort of tell them, because there was getting to be pushed back from the state, saying we don't really have an easy way to measure the methane mitigation without breaking the bank. And so coming up with this technique, and then getting that kind of moving into the actual DOI guidance is something that I think has been quite impactful, and we're continuing to do that. Next slide. And so this is actually an example of different places we've been deployed. And so the idea is, how do you have cost-effective methane emission rate measurements? And so we have our different national labs have a bunch of different different techniques to measure methane and methane concentration. And so they've been out to places in Pennsylvania and even in Hobbs. We work with different industry, like the Well Done Foundation actually is in the business of figuring out which wells are leaking the most methane and how to mitigate those wells. And so we sort of saw how they went about their practices and trying to figure out if that would be useful and the best practices for other states and so on. And yeah, it's interesting because you could actually use some of these cameras and you could actually see the methane leaking from these wells at certain wavelengths and so on. And some of these leak rates were ranging between 10 and 100 grams per hour, which was relatively small. Next slide. And so we also went out there and we started trying to figure out if we put methane sensors on drones, are we at all, is that doable? Because, we often get a question on why don't you just use satellites? And satellites are just nowhere near high resolution enough to deal with like individual, undocumented orphan wells. But drones actually can fly a lot lower. And if the wind is not too bad, we are actually having success putting methane sensors and magnetometers on drones and basically trying to map that out. So that's something that is really on the forefront of what we're doing. Next slide. And so some of the questions here are what things that are not really commonly known, which is basically just simple things like how high can you fly and still be able to detect the metal from these wells. And so it turns out that about 45 meters, if you go above that, you start losing a lot of the wells. You don't pick up nearly as many. And so I think that's a pretty useful kind of guidance of what you can get away with. And then, if you imagine around here, if you're just 20 meters above the ground, but you're going off and dropping into a canyon and all that kind of stuff, there are quite a few complexities. And so these are the types of things we're trying to figure out. Next slide. And so this is another kind of interesting story. I just kind of assumed that, oh, well, these quadcopter drones are going to be great. We know that helicopters are really expensive, and that's what's been done in a few cases, but it really does break the bank. And so that Jackson State Park, we were told, would cost about $750,000 to use a helicopter survey to try to find the orphan wells using a magnetometer. And so we thought it would be a really big victory for our program to show what we could do with quadcopter drones instead of the helicopter. And we, priced it all out to figure out how long the quadcopters can stay up and how long we'd have to have people out there. And instead of 750,000, we came up with 850,000. It actually came out worse for the quadcopter drone. And the lesson there was a lot of the researchers on our team have been using quadcopter drones, but not really surveying huge areas. But now with Catalog, we've got to survey huge areas. And so what we're hoping is kind of a sweet spot is actually a fixed wing drone, because that's something that can stay up for like 8 hours and can cover quite a bit of area and is a lot cheaper than a helicopter. And we just actually, Los Alamos has invested in 4 fixed wing drones that just arrived this week, and we'll be testing those out to basically see if those are a sweet spot for finding these wells. And so we're pretty excited to see how that turns out, because there's no reason we think they should work, because they're not too fast and the magnetometer should work just fine. And anyways, the proof will be in the pudding, but we think this could be a victory for finding these things at an inexpensive price. Next slide. And so other work that our team's been doing that would be highly impactful is just trying to see, can we kind of roughly start figuring out what are the hotspots that are more detailed than what satellite hotspots give us? And so the Department of Interior really needs this for prioritization. So can we estimate methane leak over a region using these UAVs? And so right now, the methods are only able to estimate larger methane leaks, more than 10 kilograms per hour, but we're basically trying to use machine learning to see if we can estimate methane emissions when you're just measuring it with a drone overhead, for example, to try to see if we can start prioritizing different areas to see if we have a pretty leaky site versus one that's not leaky. That type of prioritization has not been done yet at the well level. It's only been done kind of at the satellite hotspot level. Next slide. And so this is definitely, I think, right up the National Labs alley, which is trying many of the things we do, especially in natural systems, are noisy signals. And actually, something that was really interesting that was told to me by George Guthrie when I showed him this slide is he said, "Oh, this is what your dog does when they go on a walk." And I was like, "What do you mean?" And so what George was saying is that a dog actually has something like 7 different types of sensors in their nose, and each individual sensor is actually not that good. But what the dog is able to do is take those 7 kind of noisy sensors and put them all together, and then they end up with a sense of smell that's been extremely difficult for us to beat, even with the best technologies. And that kind of reminded me of a story my dad used to tell me, which is the eye is actually a horrible lens if you compare it to a lens, a camera lens or something like that. However, when the brain processes the image through the lens of the eye, it does an amazing job. And you can really, I think most of us agree, we can really see amazingly well. And so the idea of using multiple signature types to try to get what you're going after is what we're doing here. And you could argue that's sort of what nature does. I mean, nature seems to put more of its investment into the brain and how it processes things than on how it measures the individual thing, whether it's smell or sight. And so definitely for wells, we believe a combination of aerial photographs, the topo maps, LiDAR, magnetometer, and using like the latest ML methods. And I think what's really neat about this program is it can be pretty cutting edge too. I mean, one of our postdocs just got into nature machine intelligence using this technique of using, multiple noisy signals. And so it's pretty cutting edge science, but then at the same time, it's pretty impactful because it can really help you find these wells that are not that easy to find. Next slide. And so this is NETL has put an enormous amount of work into finding just the wells that are here across the country, and also coming up with, how old are they, and where are they located, and what lands are they located in. And actually they needed to do this even for projects before a catalog came along, because if you want to license a carbon sequestration site or an iWest, right, your energy transition, whether it's a solar farm or a wind farm, I mean, all of these things require knowing, are there a bunch of wells that could be problematic that are already on your land? And so they've come up with this pretty detailed database that leverages industry databases that already exist, but making this more public. And then we're plugging into this and putting undocumented orphan wells and moving them into the documented column. Next slide. And as I was saying, historical records are definitely a huge resource for us, but they are often in pretty bad shape. Actually, the picture there in the bottom right-hand corner, at least it's all typed out and it actually looks pretty clean, but I really need to get an image of what some of them really look like, which is a lot worse shape than that. And the question is, how do you extract, key things like location and depth and things like that would make our job a lot easier if we can use optical character recognition and combine it with these large language models. Next slide. And so, yes, the idea here would be, you have watermarks, you could have different things. And so we've had different people working on this, and it's been kind of fun to try to see, what ChatGPT does well with and where it completely messes up. I mean, sometimes it might take like a degree sign and turn it into a 0, and and then how do you fix that kind of problem, and more, efforts where we just say this is the bounding box where you should look for the depth and things like that. And so I think we can make quite a bit of progress quickly on extracting information from historical records. Next slide. And kind of just where this everything kind of from the drone perspective and measurement perspective is kind of rolling into these field teams where we basically have different people come to us where they, where, for example, Stonewall Jackson and also the Four Corners have already come to us and said, we have areas where we have these wells and it'd be great if you could show us how to find more of them and so on. And so we tend to put like a senior scientist on these teams, and then we have like an FAA drone licensed pilot go out, and basically we're coming up with a prioritization list because Catalog's job is to sort of realize that there isn't going to be a one size fits all approach. I mean, there's going to be places like New Mexico where visually looking for the wells is going to do quite well because our wells are not super old and we don't have that much vegetation, and we actually don't have nearly as many wells as somewhere like Pennsylvania and New York, which is overgrown with vegetation and there's almost nothing to be seen at the surface. And even if you wait till the winter for all the leaves to fall, you still can't find them that easily. And some of the areas are really hilly. And so we really want to have a matrix. We've basically come up with like a field matrix to make sure that we're covering a bunch of different types of sites. And you might not know, another big article that recently came out was how there's a bunch of undocumented orphan wells in downtown Los Angeles, and they're actually like polluting people's houses and stuff like that. And for that, it's literally under the concrete jungle. So you could imagine the drones and stuff like that are not going to work, and we need something completely different for that. And we actually have a postdoc at Lannel that's been doing a lot of work on trying to figure out how much of these wells intersect with highly populated areas. And I was actually surprised to find out that there's a lot more in populated areas than I guessed that there would be. I always pictured them being kind of in the middle of nowhere, but that's not the case because there's just a lot of places where there's oil and gas development, and then most of the oil and gas got extracted, and then people just built over that. And so that's actually quite a challenge. And so just starting, this all just started up over the last year. Our deployment teams have started going out in the summer to a bunch of different sites. And then this fall, we're going to be doing a lot more work on this. And like I said, we're definitely interested in interfacing all of this with iWest efforts because we are located, in iWest, and we have great interest in working in the Four Corners and so on. And so hopefully just you being aware of this program is useful to all of you, and I'd be happy to, field any questions or so on. Go to the next slide. Yeah, so I guess the final thing is we do learn from the states kind of like on every couple months on what they're hoping we might be able to do. And definitely one of the things that's of interest that NETL's been working on is coming up with a way to optimize well plugging, because it's just a real grand challenge to figure out how that 4.7 billion, how a state's going to get access to some of that money, and then they have a huge number of wells to deal with, and how do they basically select the wells for public plugging, and then how do you deploy your plugging and abandonment resources? If you look at how it's historically done in New Mexico, a lot of times the wells that got plugged were just simply where a company was close enough to be able to do it and that there were enough funds to do it. But the good news is there is a lot more funds that have been put into the system now. And so now everyone's kind of hiring up and trying to figure this out. And we want to try to do this in an optimum way and prioritize based on all these different things. And so we think this could be a powerful tool. Next slide. If there's one. Yeah, well, that's what I had. So I hope that this was of interest, and I'm happy to field any questions.
Thank you, Hari. That was great. There is a question in the chat. There's a couple, actually. I don't know if you can see them, but I'd be happy to read them.
So do you want me to just read the question and then try to answer it?
Sure. Okay,
so I guess the first one is, do we know the impact of methane leaks on plants and impacts on growth and community structure? And so my guess, so that's not something that we've directly been looking at. I mean, it'd be unfair to say that catalog is the only, there's been a lot of work done on methane leaks and everything before our program started. And definitely people have been looking at the impact of methane on different things and growth and community structure. So I'm pretty sure there would be quite a bit in the literature. But our job is basically to find these wells and just make sure that the methane stops leaking. And so that's something that we haven't been focusing on, if that helps. The next one, many of the wells in the Four Corners area are historic spills. Emissions are from undocumented, spatially pipeline gathering systems built in the 50s, 60s. Could be steel, fiberglass, even surface flow. Not, yeah, right. I think of the wells. Yeah, no. And so it turns out that that is the reason why things like just magnet, it's got to be trying to be quite clever about and remember that in addition to just these undocumented wells leaking, the documented, the active oil wells actually leak quite a bit methane too. That's not what our program's going after. But then there's also all the pipelines and everything that leak methane. And so the bottom line is all of those leaks really do need to be dealt with just because of how bad a warming gas methane is. And so you're absolutely right. I mean, there's going to be magnetometer is not simply the answer. And so we're really hoping that we don't know the answer yet, but we're hoping that by using, you can put multiple measurement techniques on a drone or drive around with multiple measurement techniques and try. So far, most scientists have been just working on one signature at a time. And so we think there's a lot of value added in combining multiple signatures to find these things. And so that is one of the things we're going after, quite seriously. Would it be worthwhile, especially in the Southwest, to use crowdsourcing for some? Oh, that's a great question. So I did not, I did not have a slide on this, but there's a citizen science work package that we're trying to stand up on this program, which would actually involve kind of like a well finder app because it is true that a lot of people have found these wells just because they happen to be in their backyard or something like that. Definitely in Pennsylvania and New York, that's been a pretty common thing. And so, the low level version of that would be you suspect something could be a well that's on your land or something like that, or even turn it into a game like you're talking about, like geocaching or something. And you take a picture of the well, and then you basically and then the other part that's actually more interesting is cell phone nowadays actually, I didn't realize this, but they have like a crude magnetometer and other measuring devices that we can tap into. And so we actually, at Sandia, they actually used their cell phone and went out to an abandoned field where there were wells buried, and they were actually able to detect those wells with their phone. And so we're in the process of trying to figure this out. It's a bit more complicated than some of our other work packages because there's safety considerations, right? You can't just have someone out there looking for wells and then perhaps have something bad happen and all that. So we're trying to work through all of that, but we do think that a citizen science component would be quite powerful for this and could be quite successful too, especially there's a lot of crowdsourcing for the earth sciences, and seismology and all these different things, and it's been quite effective. And this seems like an area where it would be good if we can get through all the safety hurdles and so on. Yeah, so exactly what you're saying here, open to Google. And so we are definitely looking into that. App is a great idea. Communicate app. Yes. And so definitely this is bill funded work. And so the thing I haven't mentioned is catalog stood up in the first year to just be these 5 national labs, but there is going to be a FOA for universities to participate. And we want to have a lot of university collaboration and, even minority serving institutions, definitely. A lot of the wells are actually in areas where there's lots of overlap with lots of colleges and so on. And so it's pretty nice because there's a nice fieldwork component. Machine learning is a hot topic. And, I think most, at least even me, I like drones. I mean, drones are just neat. And so I think it's a pretty good student project, which could have pretty cutting edge science, but it also has a lot of neat aspects on two hot areas, which are both, drones as well as machine learning. And so I think it has a nice mix of things that work really well with universities. Okay. I can finally be quiet because I've been talking nonstop, but I guess there's about 5 minutes left. And if anybody else has any questions, I'd be happy to answer them. You could even chime in on the mic if you want. Is that how it works, or you only do chat?
Yeah. Yeah, feel free to go off mute if you have a question or comment for Hari. Well, maybe we can have you back on, Hari, when you stand up the app, the citizen science app. That would be a nice feature for the region.
Yeah, no, for sure. And I think, like I said, I think the Four Corners will be one of our big areas that we're going to be doing a lot of work. And it's definitely of interest to us for multiple reasons because of the complicated patchwork of tribal and federal land and everything, it being a methane hotspot. And, how are our techniques going to work when you've got multiple sources leaking methane and trying to find these wells within sometimes an active oil field and things like that. And so, yeah, there's a lot of good reasons to go after the Four Corners for us. And I think iWest has a lot of interest in that region too.
All right, well, thank you, Hari, and thank everyone for joining us today. Heads up about the next seminar on Wednesday, September 27th. We'll be hearing from Noah Eckert from D.E. Shaw Renewable Investments. He's going to be telling us about the San Juan Solar and Storage Project in the Four Corners region. So I hope you'll tune in. And with that, we will end and see you next time.
Thanks for attending.